It's my pleasure to introduce to you our last speaker of today. This is Professor Tim Swaggart, who is at MIT as the John D. MacArthur Professor and also the Faculty Director of the hope I can do it right, Deshpande Center for Innovation. And when it comes to innovation, this man really knows innovation. And why I say that is because he is one of the winners of the if I can do it right, Lemelson MIT Innovators Awards, which carries a $500,000 prize to it, which is pretty hefty indeed. Tim, indeed, born and grew up in Montana, and we're delighted to have him today. He is also a teacher scholar of, I think, 2007, something like that. Or is that?
I think it was early 90s.
Early 90s. Oh, okay. I'm wrong.
Oh, I look so young.
Okay, I don't know. And he's gonna speak to us today on molecular designs for specificity in chemical sensors. And if you can't sense it, well, what do you do? What do you know about it? Okay.
Okay. Great. Thank you, Dick. It's always a pleasure to be introduced by one of your chemistry heroes, and so it's really a pleasure to be introduced by Dick. And it's also really an honor to be here as an invitee for the Dreyfus Foundation, which I think we've seen many testaments to it today. But I work in a building called the Dreyfus Building. It was actually just given a little tiny video clip in the thing, and recently they actually helped us beautify the building by the Dreyfus Foundation by helping us augment the lobby of it, which is now a big focal point. And as mentioned, I also benefited from a Dreyfus Teacher Scholar Award when I was an assistant professor at University of Pennsylvania, and also have received a postdoctoral support from for the energy-based postdoc at MIT. So the Dreyfus Foundation really, I think, fits a unique niche where there really that it funds just basic chemistry and chemical engineering. And I think that chemistry and chemical engineering, when I was a graduate student, were like this. Now they're getting closer and closer together. And I think that it's great to have an organization that really recognizes and helps to keep that bridge going. Okay. So today, I thought I'd start with things that basically kind of where we were when I got my Dreyfus Teacher Scholar Award, and it was as an assistant professor. I was working on a idea, kind of an inspirational idea, that something we haven't really realized in its purest form, and probably never will, is to create chemical sensors that you could imagine being formed by a single molecule wire or a nanowire that you can make and bridge to electrodes with. And the scheme was, it had been inspired by work I'd done on conducting polymers, where I found they were really sensitive to their environment. I thought, boy, if I can make a polymer or something here that has these carriers, I mean, you have to put charge through the system to create the circuit. So these positive charge there, or you would call it a hole in semiconductor terms, but it kind of has to run around this circuit to get conductance. We can measure the resistance. And as it runs through that, it's going through every one of these little units. And what I've done with these units here is the idea was, let's put some recognition element on them. We'll call it a receptor, like things lock and key type recognition schemes that are used in biology, but maybe things that are a little simpler because we're not quite as clever as biology. Let's put these receptors on them, and let's design it such that when something binds to that receptor, it dramatically changes the property of the local unit that it's attached to. And the fact is, they can make it to where it makes it inhospitable for this cation to be on it. And that is, it would create a barrier to the transport through this. And in this way, if we have millions of these all wired in series, by just activating one of them, we can bring down the whole circuit. So it's like having all these light switches flipped on, and you're just turning one of them off. And that will give you signal gain. So the idea was, can wires in this capacity be wired up to give a signal gain? And so this was an idea that I was kicking around when I started in 1990. And we did a lot with different polymers, having fun with this coupling of recognition to the polymer backbone. And here are just a couple early examples from my group where we did a fair amount of chemical synthesis in these types of schemes. Here's one where we basically make use of a conducting polymer called polythiophene. Okay, and you can put the cations in there, that we call it a hole, and they can run up and down this backbone. But we have this loop on it here, this chemical loop, which is inspired by work from Fraser Stoddard, one recent Nobel laureate, that is known to bind paraquat, which is a known herbicide. It's a nasty compound you don't want to ingest. And so the idea is that when this paraquat now binds into these little hoops here, shown here, we create one that now is different, and it creates this energetic barrier. And that barrier has two origins. One is this is an electron acceptor. It basically pulls electron density away from the polymer backbone, making it harder for this cation to be there. And also this has two positive charges of itself. So there's just a natural electrostatic repulsion here between this carrier coming through the system and the guest. Okay, so we get dramatic changes in conductivity in polymers like this when we do this. Here's another example that has something a little different. What we did here is we made a fluoride ion receptor, making use of these porphyrins that have what we call a cyclophane structure around them. And so we cap them top and bottom. So here's a porphyrin in the middle, and it has no metal in it, but it has these amide NH groups and these other hydrogens, and those create positive charge, which interacts strongly with ions. And this structure may not be so easy to see in this line drawing, but when you look at this in a three-dimensional figure, what you see is there are little caves in here that are really quite tight. And fluorine is the smallest anion that you can have, and fluorine could sneak in there, but no other ions can get inside of that. So this has perfect selectivity for fluorine, and it's a big sponge for it. So when the fluorine ions get in there, they're negatively charged, and so now they create an electrostatic pinning potential, purely pinning potential. That is, they create a large negative potential here. They bind cooperatively. That is, when one goes in, it sucks the second one in even better. But they create a large negative potential here, and when these holes come along, they get stuck over the top. So this is kind of like just now creating a blockade by sticking things here in the middle of this. And this also creates a really nice way to make fluoride ion sensors. However, neither one of these really addressed my dream scenario, because these were continuous films. And we went on to do other things in using photochemistry to demonstrate molecular wires amplify. We did that back in the mid-90s, but we never really realized this electrical scheme in its purest sense. And there are a number of reasons for that. One is that trying to make really robust junctions between single molecules and metals is still not so easy. We can put sulfur in there that binds strongly to gold, but this is something that has to stand up to changes in humidity, temperature, stresses, air, long periods of time, and quite simply when you're going to have changes in resistance. You have a natural feature of any molecule or semiconductor that's put in contact with a metal. It's called a Schottky barrier. That comes just because of equilibration of the electrons flowing one way or the other. And those barriers can be sensitive to their environment also. And then you also are fighting the second law of thermodynamics, because if I have this strung, it looks like some nice clothesline out there, but that's a high energy state, because if this polymer has any sort of flexibility, which it needs to have usually to kind of be able to kind of manipulate it and make solutions of it, it's trying to coil up on itself. Okay, so we have it in a high energy conformation, and any sort of interactions with it are trying to make it basically lose this organization. So this is a high energy state that is fundamentally unstable. Okay, so we really wanted to go after these molecular wires, and decided the best route was to go with a different scheme and to use intrinsically, essentially shape-persistent objects. And carbon nanotubes were an ideal type of structure for us to do this with. And we also decided we wanted to be practical. We wanted things that had real-world applicability. So we want things that we don't have to have a single wire. I mean, people have done this. I mean, it was famously done by Hanji Dai at Stanford initially to make single wire devices, but it's hard to make them in mass in a scalable, manufacturable way. And so what we wanted to do is to take dispersions of these nanotubes and essentially deposit them in some kind of disordered arrangement here, and yet they still provide these, you can see little kind of pathways where you could maybe take electrons jumping between nanotubes and get from one electrode to the other and make our circuit. Okay, so the advantages of this type of arrangement and why we're so interested in it is that you can make very low power and low cost sensors this way. They, we're really good at making small electrodes. That's what the basis of your laptop computer are. We can make these in mass. And also they're really naturally to put into wireless networks to give us interconnectivity. Now, the nanotubes tend to be what we have p-doped semiconductors. That is, so when we think about this, the carriers have positive charges. And if you have strong, dipoles with negative charge, they'll interact with them. We usually have to put something around these nanotubes. We do it in some sense to solubilize them, to make them so we can disperse them and actually deposit them with a pipette or something on here. But more importantly here, this little corona here is going to give us chemical selectivity. Okay, so everything we're going to do when we modify these nanotubes, we do it so we get chemical selectivity. So one of the things I like to say about nanotubes, carbon nanotubes, they're great sensors. They respond to everything. Okay, that means you have a very high noise level. Usually, you have a noise level, and so what we need to do is bring the chemical signal that we want way up over noise, so we can see that signal. And so, in doing so, we have to think about what are the different mechanisms that these carbon nanotubes use to give signal transduction, or how can chemicals change the electrical resistance through this nanotube. And I already mentioned you can have these shocky barriers, okay? I mean, the good thing about the nanotubes, they're big enough, they lay on these electrodes, they don't tend to move around, but you still are going to have these shocky barriers, okay? And we worry about those. And we often passivate these. We put something over the top that just to make sure that they're not there. So they haven't been problems in any of the things I'm going to tell you about today. But then we have two other modes that we can do. The first is very similar to what I showed you with my initial kind of wire scheme. That is, can we have our analyte, the molecule we're looking for, kind of interact directly with the nanotube? It can basically behave like kind of a sticky thing that holds the carrier and prevents that cation from moving through the nanotube. It can donate electrons to the nanotube and therefore essentially annihilate the carriers. That is, it just can add electrons and the carriers go away. Or it can also be used to induce new carriers. I'll show you examples of all those. There's also this idea that when you make these devices the way I want to, so we're not making the single wire anymore. So when we don't make the single wire, we have junctions between them. And at these junctions, the electrons have to hop from one side to the other, okay? And if these electronic systems are not kind of completely fused, there is a little gap. So it's like jumping over a stream. And electrons can do that. It's called tunneling. They can go through these, and tunneling falls off exponentially. The probability that you can do that falls off exponentially with distance. So it's very sensitive to the distance. So if you have something here, if you have something that just swells the network just a little bit, you can change this distance between the nanotubes very, very gently and get an effect. So let's first just talk about how, making dispersions of nanotubes. And nanotubes tend to be very insoluble. In fact, in the early days of nanotube research, a lot of it was just about how do we keep these things in solution and process them, because they tend to form these bundles where they have very strong interactions, van der Waals interactions between the nanotubes. And so usually what we do is you'll sonicate them. You use ultrasonic energy to essentially break them apart. And then you'll use something like another polymer here, this is being polythiophene, a very highly polarizable polymer that really likes the nanotube surface, that's there in, waiting around to essentially loop it up and basically create this corona. So this is just a molecular model of polythiophene wrapping it. And notice that the nanotube is not binding covalently to it, it's just phys-adsorbed. And if you do this with high molecular weight thiophene, you can make things that are stable for years. So this was great because we were working with engineers, and we would prepare a sample and they would say, okay, we're interested in printing this, but we might not get to it for a month. And you leave the sample with them, and the sample has to be good a month later, okay? So we did that. Now this is kind of a boring polymer to use, but you can do the same thing with polythiophenes that we've basically modified to make now things that are starting to look like receptors on them. And so here's one that uses something called a calixarane. It has the shape of a small bucket type molecule. And when you put terp-butyl groups here, these are big hydrocarbon units. What you can do is you can find that these will bind xylenes. These are different isomers of xylene. The one that has the methyls on the two termini is kind of longer and skinnier, and it fits very nicely in this bucket. We determined binding constants in solution of this, but the ortho and meta versions of this do not fit nearly as nicely, so they don't bind as well. Now it turns out this corona here, the xylenes also can kind of solvate that. They can kind of swell it, so you have some non-specific interactions, but then you have the specific interactions. But what we found that if you start now looking at devices like this, where we have that corona that has this and we expose it to xylenes, you find that we get the biggest effect from the paraxylene, the one that binds the most. It partitions more heavily into this film. And so what I'm showing you here, and I'll show you more data like this, this is G here. It is what people use by convention for conductance. It's not free energy. It's not Gibbs free energy, which you heard about in the last talk, but this is conductance. And so what I'm doing, we normalize it. So at 0, just is saying that that's kind of your baseline here. I got a negative sign here because every time I give it a little whiff of these vapors, where the inflection point is here, the conductance or the amount of current that's flowing through here at a fixed voltage goes down. So that's why we have a negative sign. And it goes down more for the para than for the meta and the ortho. And that magnitude goes directly with the binding constants we measured. And then what you see is after we in the gas, there's a desorptive kinetics here. Initially, some of it just comes off, and then we have some that's bound more tightly that has first order dissociative kinetics. And so this is actually quite good. It's actually not trivial to make a sensor that differentiates between xylenes on a molecular basis so simply because these all have really marginal dipoles. There's just differences in shape, okay? So that's interesting, but maybe, there are other molecules that are more important for us to look at, particularly toxic things that we think about would be nice to wear as have a badge if you're working in a situation, a place where you might be exposed to these toxic chemicals. And one in particular is carbon monoxide. Now, carbon nanotubes, if you have them free of metal, do not interact with they do not respond to carbon monoxide at all. There's zero background from them. But we're looking for ways to do this. And carbon monoxide binds to transition metals. It's very well known in organometallic chemistry. And here is a paper from some years ago that I thought was really quite interesting, where they showed that if you make this cobalt compound, that this amine ligand would reversibly come off, and it would go back and forth, but if you have carbon monoxide around, the carbon monoxide would essentially park itself at the same place where it was bound and favor the equilibrium on this side. And this is very nice because these amines have a lone pair of electrons, which is a good donor. And so when we have these cations in the nanotube, that amine essentially is like a little tractor beam, or it basically locks on them, donates electron density, and pins them, and also compensates for the charge and de-dopes the nanotubes. So we get a very big effect when you have amines that interact with carbon nanotubes. So in this case, we're trying to harness now a equilibrium that works in solution. This does not work in the solid state. So we had to make a sensor that kind of emulated chemistry in solution. I'll come back to that again later, but here's a case where we put this fluorocarbon oil, put this chemical in it, over the top of just some naked nanotubes that we disperse down. And now what you see is we get essentially perfect selectivity for carbon monoxide. And either other things that might have kind of similar back bonding characteristics for the organometallic chemists in the audience don't seem to really give us any effect. So acetylene and ethylene do not give us a big effect. So that was nice. We had something that had near perfect selectivity for what we wanted to by basically looking in the literature at all the kind of wonderful chemistry that's out there that people have designed. Now, we have a very interested in strategically looking at agriculture and how we can use gas sensors to reduce food waste, improve agricultural production, and just logistics and how you get food to different places. And so one of the gases that's most interesting there is ethylene, which is a universal plant hormone. It controls when fruit ripens in particular, and you can actually use that as kind of a mechanism to understand ripening or in batch level, whether it's at a grocery store, but also in your storage of the food, knowing that when things are going wrong and they're starting to ripen. You might have heard the saying, it takes one bad apple, right? We're really usually referring to somebody at a party that's messing up the party, but it really takes one rotten apple in a batch that's giving off ethylene to cause all the apples to ripen really rapidly, because the ethylene will upregulate all their enzymes and they'll start to ripen. So apples are an example I'll come back to in a bit, but here I'm just showing you kind of a ripening profile for a pear and how you can see how you have a big inflection at the ripening of its ethylene emissions. So to solve this, we again employed organometallic chemistry. We made use of some chemistry that was developed by Diaz at UT Arlington, where he made these air-stable copper ethylene compounds. Okay, there are not a lot of air-stable metal complexes that bind ethylene, and this is kind of unique. So it binds the copper in a tetrahedral form, and it has these trifluoromethyl groups that basically withdraw electron density and make this nice and air-stable. So what we do is we initially make the copper that has a very weak ligand. We have toluene bound to it, and then we react it with the nanotubes, and it sticks the nanotubes. Whoa, caught it. It sticks to those nanotubes like glue, okay? So it sticks to the nanotubes, and now we have nanotubes that are functionalized, and we're not really sure. Nanotube research is tricky because unless we can sometimes make fullerene compounds, but we can't take NMRs of them. We have no crystal structures. We have no mass specs. We do elemental analysis by X-ray photoelectron spectroscopy. We do thermogravimetric, infrared, Raman, but we're not really at the same level of characterization you have in the molecular world. But nevertheless, what we believe is happening is this copper sticks to the nanotubes. One of the ligands comes on and off. That's actually very well known for these type of scorpionate ligands. And it senses ethylene. And now we get a very robust response to ethylene. Nanotubes without this do not respond to ethylene. And we actually went on and did a whole study. You can look at it in this paper, a whole study of fruit ripening over a week's period, different fruits, different temperatures, showed all the profiles. Not all of them have this big hockey stick. Some of them are more gradual in how they go. Some of them go up and go down. But we went through all these different fruits, and we were able to nail their ethylene with this single sensor here. Okay, and that's kind of important because if I blindfolded you and I put a banana and a pear to your nose, I think you could tell they were different. You're not smelling ethylene, you're smelling esters. Those are polar compounds, and they actually have a native, stronger interaction with the nanotubes and ethylene. So they're giving some noise, but we're able to bring this one signal up over that noise considerably. And so we were excited enough about the opportunity with this, we went and started a company called C2Sense, and the first product that was launched a couple years ago was for Apple cold storage rooms. Again, when you buy apples in August, it isn't that they came from South America or something. They were probably, grown not too far from where you're living, but they were, well, you're certainly in the northern United States, but they were in a cold storage room for the last, 9+ months. They were in a cold storage room. They were cooled down. There was an inhibitor applied that actually helped to essentially inhibit the enzymes that were activated. But the key thing is, in every one of these cold storage rooms, is about $1 million of apples. And so you want to know if the ethylene levels were starting to come up. If they didn't get them, you didn't get them fixed, and even though you cooled them down and you depleted the oxygen in there, they can still start ripening. If there are a few apples that are too ripe, and you need to know that, and you need to know, am I going to store them or am I going to make apple juice? Okay? And so now these sensors are used in those facilities and for monitoring cold storage of apples. Now, we're all familiar with the transistor and the power of it, and the real power of the transistor isn't that there's just one of them, it's that there are millions of them on a chip, okay, and they're all working. So it's natural to think about the same thing and taking this is a field effect transistor variant of our sensor. We use those often to do mechanistic work as well as actually to augment our sensing, but nevertheless, it's natural to start thinking about making many different sensors. And this is actually kind of important because even though I've been highlighting some very big gains that we can make in terms of selectivity, we're not perfect. I mean, the only recognition elements that are really close to perfect is DNA. And all synthetic receptors are really imperfect. And so you're going to have what we call cross-reactivity. So you might make a sensor array here, but you're going to get, from each sensor, you're going to get a little different profile. You might have different temporal or different time dependence to them, different magnitudes. But there is nevertheless information there, and it's very similar to olfaction or taste. That is, we do not have receptors for coffee and chocolate. We sampled those once upon a time, and our brain did a calculation and remembered that. So every time we do it, our brain is doing a calculation with some data that looks like this and telling us that's chocolate, that's coffee, okay? And so you can do the same thing. You basically take this data and you do a linear algebra on it, and we tend to use kind of the simplest type. We do principal component analysis, where you basically take linear combinations of the data, you solve for orthogonal eigenvectors that have maximal variance, and then you plot in this reduced dimensionality space. So each one of these peaks are now linear combinations of responses from a variety of sensors. And so to do this, and this is not new. I had a review on the last slide that was from David Walton and Nate Lewis that were real pioneers in this area. But the area I would honestly say is stalled out a bit, because if you do not partition chemical space broad enough, you can get a lot of false positives. It's hard to get a sensor that isn't spoofed. And so we decided, let's see if we can start now taking this a step further and start parsing out chemical space in kind of a logical way. Let's put on things that have hydrogen bond donor capabilities, things that have hydrogen bond acceptors. So if you think about putting a hydrogen right in the middle of this ring, it can hydrogen bond all those oxygens. Things that just have some kind of characteristic polarity. I mentioned the Calixarenes before. They're these little bucket compounds that are nice for binding aromatic and chlorinated hydrocarbons. They're very good at doing that. And then maybe just things that are hydrophobic. And initially, we actually made things that responded to water. We've actually decided humidity sensors are so ubiquitous and cheap that we can't compete there. That's a very mature science. So we just buy humidity sensors now. Okay, so how do we put these on? Well, we developed some chemistry, and what we needed in this case is we needed chemistry that really we wanted to put things, anchor things very robustly to the surface of carbon nanotubes. Now, the problem with that is if you're doing that to a single-walled nanotube, so every nanotubes I've shown you right now are just a single tube, you kill the electronic structure and they become poor conductors. But there is another type of nanotube called multi-wall nanotubes that have these onion-like structures. And so what we do is we use this chemistry essentially to saturatively chemically functionalize the surface. So this reaction that we have here, if you're interested, you can look at that paper, is really good at stapling a very high density of these functional groups all over the surface. And once we have those, we have 2 functional groups per unit. We can do chemistries like the famous click reaction. We can do cross-metathesis chemistry using Bob Grubb's catalyst here, or we can do free radical additions across these alkenes. And so I just want to draw your attention to the one that's a long hydrocarbon right down here, where we can hang long hydrocarbons, make a very hydrophobic one, and also this one where we now put this hydrogen bonding group. But And when we look at those different functionalizations in our sensors, you can see that they behave as expected. So here again is that conductance change. Here's the one on the side that this one that has the biggest response is the one that just has the pure hydrocarbons on the multi-wall nanotube, and it responds most a decade. So what's happening here is we took these multi-wall nanotubes, we took the outer wall and we just saturated it chemically, so it's an insulator. It's essentially, think of it as insulation. It's like a sponge that absorbs it. So when it absorbs it, then they tend to expand slightly. So what we are really doing is we have something that's purely a swelling mechanism that's changing the distance those electrons have to tunnel between the two tubes. And so naturally we get an increase in resistance between the nanotubes. Now if we go to pentanol, now we see the one that has the hydrogen bonding characteristics, that now it wins in a very big way because it sequesters more effectively the pentanol into the corona around these nanotubes, and they swell more. And the other thing I want to show you is that the multi-wall nanotubes do not respond at all. So you have to have this functionality to make them respond. And they're also very, very robust in terms of they always come back to baseline. We anneal the sensors at 130 degrees overnight before we start. And that's very important because the next step you want to do is you want to take this matrix of all these different types of functionalizations we have, and you expose it to a whole bunch of different chemicals, and you can do this at different concentrations, and even you get fancy and have mixtures of them, but you create a training set, and then we do, again, that linear algebra trick on these to get reduced dimensionality plots like this. And so now what I have is these different things circled, okay? These are different kind of classes of functionality. We're not doing fragrances from beverages and food, but what I'd like to convince you is that this actually does parse out chemical space in a meaningful way. And so you might look carefully here and you say, okay, you have these aliphatic or just purely hydrocarbons there, alkanes, and now I'm kind of drawing my other circle here that has esters and ketones, but these are really right on the border right in there. Let's look and see what they are. The squares here are dihexyl ether. That is, you have two C6 alkanes with one oxygen in the middle. So it really should be there because it looks a lot like an alkane. This is 2-decanone. That is a C10 ketone. It's a lot more like a hydrocarbon than it is like acetone. This right here, that one, that is 1,3,5-trimethylbenzene. So it's aromatic, but it has methyl groups around its periphery, making it look like it's a hydrocarbon. And this is octanol. So this really faithfully kind of represents chemical space. And so I think there's a long way to, many different ways to start refining this more. But it is getting possible to make these olfaction methods to be more robust with proper chemical design. Now another thing I've actually mentioned early on was that these could have very low power. And it takes very few electrons you have to move to make a resistance measurement. Okay? In fact, it can be so low power that you can use a cell phone, your smartphone, to inductively power the sensor and read it. And this all works through digital types of signals that electrical engineers have mastered. And your smartphone will put out some signal here, and this is an antenna. This is called a passive radio frequency identification tag, or RFID tag. It's just has a resonant frequency that is determined by this antenna and different resistances and this capacitor that's been put in line here. And so what happens here is you can now power this with your smartphone. It has an integrated circuit in the middle that basically can talk back to your smartphone, gives it digital signal back, and basically tells it a serial number. Just very simple. It just says, I am sensor 1234. Okay? So what we did with this is we decided, well, let's see if we can make sensors out of these that can be read with kind of off the web software that you can upload on your smartphone. And what we did is we just hacked it by punching a hole in the circuit. So we disrupted the circuit, so we ruined this frequency that it was adjusted to. It was adjusted at 13.56 megahertz, where your smartphone goes. And then we reconnected it with nanotubes. And we can reconnect it with nanotubes where we put enough nanotubes in there that it doesn't know that it's been adulterated, and it works again. and then we can expose it to a chemical which changes the resistance and it doesn't work. Or we can start with one that isn't quite conductive enough, so it doesn't really work initially, but then when you activate it, it works. And so we've made these kind of simple, binary types of sensors like this. Using off-the-shelf smartphone. Now, it doesn't have to be binary. We don't know how to program smartphones, so that's why we're doing binary right now. But even this binary sensor has utility, and I want to demonstrate that to you by playing a little video that my student Joe Azzarelli, who was on this project, did that shows that. And here's the video.
On the left, we have an unmodified control tag. This tag will always be readable. On the right, we have a sensor tag. This tag will only turn on in the presence of an explosive. Notice how the phone does not read the sensor tag when the box is empty. Now I will place an improvised explosive mimic into the box. This mimic is chemically equivalent to many common explosives. Again, scanning the control tag indicates the system is functioning properly. Now, with the explosive material in the box, the sensor has turned on, and we see the message verifying that an explosive material has been detected. This information could automatically be relayed to the authorities.
So one of the things that's important about this type of method, particularly when you couple to smartphones, you have spatial, temporal information in addition to the sensor information. And so we're really interested in, smartphones right now, they're just telling people what we want to buy or where we like to eat dinner and how fast we're moving on the freeway. But wouldn't it be great if they could say, you're being exposed to pollution. You can create attribution to that. You can create models. People can start understanding where it's coming from, what's going on, and whether it's in your home or at work or wherever. So we really think that this digital connectiveness is very, very important. Now we've taken this further. I'll just leave you with this paper here, but to develop other sensors that can be used in food packaging. Okay, turns out these RFID chips are a little too expensive for food packaging. We're working on cheaper alternatives that don't have the integrated circuit in them right now. But here's a case where we actually developed sensors that you can have non-line of sight. You don't have to see it. It just can't go through metal. But you can basically interrogate the internal contents of produce. Now, when you go buy produce in the grocery store, when it's in these packages, those are called modified atmosphere packaging. They're meant to keep oxygen out and give longer shelf life to the produce. But sometimes you bring these things home and you open them and they'll smell very foul. That's because that failed. So wouldn't it be nice if you could have dynamic expiration dates? You don't throw things away just because it says expired. You actually know if it's actually good or not. And so the way we've done that is we actually have this platform where we have another polymer that goes around the nanotubes. It has pyridines on it, and we put iron 2 species, or iron 2 salts, just simple salts in, and bind them around the nanotubes. Now, iron 2 is air sensitive. It tends to oxidize the air to iron 3. So we do this under inert atmosphere, and the iron 2 is strongly reducing. So the iron 2 donates electrons to the nanotube, and it becomes very insulating because we've killed all the holes in it. There are no holes. And so the nanotubes are now insulating, but if you give it a whiff of air, it now starts coming up and becoming conductive. Okay? So we have an oxygen dosimeter that you can use for food packaging here. So that concept of having a metal go from one oxidation state to another, changing the conductance, is really important. And it turns out there are many different catalytic cycles that people do in organometallic chemistry that involve what we call oxidation, oxidative addition, and reductive elimination. And we think of the metals as going between different oxidation states. And so it's very natural now for us to start thinking about, can we start taking, brilliant, catalytic chemistry like we heard from John earlier this morning, and now start taking those methods and using them to create sensors. And so we decided to start this with something pretty simple. It's called the Heck reaction. It's what Richard Heck received a Nobel Prize for. And in this case, we have a catalytic cycle that goes through here. And the ones I have circled in red are the two resting states of the catalyst. That is the states that's where the catalyst kind of resides. And so if we don't have any of this RX group, the thing that does this oxidative addition, we have the palladium in the zero valent state. That is, it can be kind of reducing. But if this is around, it will oxidize it to the palladium-2. So let's say if we have some of this halide around, we'll basically have this be the resting state. And now if we feed it some of this alkene, it'll quickly zip these species. It does an insertion, beta hydride elimination, and then deprotonation. It'll quickly generate over here and then slowly bleed back to this state if we have an excess of this around. Okay, so what we can do is we can make a sensor. If we had a bunch of this around and none of that, we can make a sensor for the halide, or we can make a sensor for the alkene. So in this case, if we have the palladium all in this state, every time we add some of this alkene, it's going to make some palladium-0. It's going to reduce our nanotubes, change the conductance, and then it'll gradually come back over here and the conductance will go up again. So we'll bring the conductance down by making palladium-0, bring it back up by making palladium-2. Now it turns out we've done this in a classic sense with aryl halides, but the system that works best is a system that was invented by Shannon Stahl at University of Wisconsin, where he came up with something called the oxidative Heck reaction. So instead of using an aryl halide, he uses this boronic acid, which in the presence of oxygen essentially conducts that first step. So it basically takes the palladium-0 and puts a benzene ring on it, okay? Or a phenyl ring attached to it. So what we did here, this is Shannon's favorite ligand, the one that gives him the highest catalytic rates. It's the thing that binds to the palladium. We have the boronic acid, which is which is the substrate that's going to basically keep taking the palladium-0 and put it into palladium-2. And then we have an ionic liquid composition. This is a palladium source. And this is just a little solvent that we use to get everything kind of mixed up nicely. So let's see what it does when we put it in our sensor, and it works really quite well. So what we have here now, this is a decrease in conductivity here. I'm plotting it kind of the opposite way when I've shown it before, but that's the way Vera wanted to do it. And without the palladium or without other things, we get really no response. If we throw the palladium in there and we leave out this ligand, we get a response and it's completely irreversible, because what we do is the palladium-0 is not stable under those circumstances, and it just makes colloidal metal that sticks to the nanotubes, and you know, this is what you get. So all the palladium got taken out. But if we basically put the catalytic mixture that Shannon put together here, and we do that, when we add our alkene ethyl acrylate here, which is a toxic monomer that people use on giga scale to make polymers, what we get is we get a really strong reduction in conductivity, because this again is taking the palladium-0, going around that catalytic cycle and making some the palladium-2, excuse me, going around that catalytic cycle and making some palladium-0, which is killing the conductivity, and then this starts reacting with it and bringing it back. Okay, has reasonable linearity that you would like for analytical chemistry, makes the OSHA permissible limits. But one of the things I think that is really interesting that Vera did is she went through and she looked at all the ligands that Shannon and palladium sources that Shannon and his group had studied, and they had different yields for their reactions here. This is the yields from his experiments. And then she plotted her sensing data. And what you see is this one over here, number 1, gives us the largest response, and it's the one that gives the largest yield. We have an anomalous situation here with palladium acetate and this bipyridyl. We think there's kind of a side reaction going on there that's giving us this large signal. But nevertheless, this really mirrors what Shannon had found, and also it has very good specificity. Reactive alkenes like ethyl acrylate here have very large responses. But if we just have the same, this is again the polar end of the molecule is what usually interacts strongly with the nanotubes. If we just take, you know, its close cousin here that's just missing this double bond, you see we're really at baseline. So we actually have a way of getting very high selectivity by making use of organometallic chemistry. So with that, it's time for me to to close here. Hopefully I've shown you that carbon nanotube gas sensors have some real promise. They can be very low power. I think that we're really the place, if you understand, by looking at what's going on broadly in chemistry, we can start taking these other, you know, selective reactions that people have designed to do chemical transformations and essentially parlay these into sensor responses. And in fact, as we even dream that maybe our sensor would become so good that they could become a discovery method, so that John can screen his chemistry by making a chemi resistor here. That might be a little bit of a stretch right now, but if you want to try it, I'll be happy to play with you on that. And again, it's like all of us, I don't do any of this chemistry. I'm surrounded by motivated, highly intelligent, dedicated students. Command a small army of them. I feel very privileged to have that. And this is the group that did it. The names were at the bottom of the different slides, and not all of the people that I talked about are in this picture, but I'm really grateful to have them and working with me and doing the hard work. And thank you for your attention.
Questions, comments? Yes.
Great talk. I was wondering how reversible the interaction of this analytes are with the nanotubes?
Yeah, so there are, so I kind of skipped over a couple things. So the last one where we're doing the Heck reaction, it's reversible until you run out of boronic acid, right? You're eventually going to consume the boronic acid. But so the sensor will have a lifetime, which is chemically in there, okay? But we're doing ultra trace sensing part per million, so it takes a long time before you get rid of consume all that. Other ones are completely, sometimes we want to make things that are irreversible. So the oxygen for your packaging, your food packaging, what you really want is a dose, the total dose of oxygen that came in. So that's a dosimeter. The iron's being oxidized irreversibly is giving you essentially an integrated readout. Also, if you're making chemical safety badges, okay, let's say you have a rate of change that your sensor can be monitoring, so you know that if you're being exposed to something that's really an immediate threat, but you also want to know your cumulative dose, right? So having a dosimeter, again, it's a chemical integrator. And also in doing so, you actually get higher sensitivity. You can get instantaneously, you get a bigger signal over a period of time. So sometimes we purposely try and make irreversible sensors that are, you properly call them dosimeters, and sometimes we want them to be reversible. They're both types that we go after. Depends on the application.
So one of the amazing selling points of these devices are their massive scalability, and a lot of the applications you've talked about could take advantage of that. Are there any issues with disposal of these materials, right? So if you have a whole bunch of solubilized nanotubes. So
first of all, the nanotubes, I don't think there's really a environmental problem with them. The fact is, there have been a number of studies. They haven't. I mean, the big thing is actually having agglomerated particles that are like this, that look like asbestos that can get in your lungs. But nanotubes themselves have not been shown to be problematic, to my knowledge. And I've had some colleagues that have looked at this that want to implant them in people. I'm not quite that way, but I don't think that they're going to be used in micrograms or less per sensor. Okay, so they're very small amounts. They're nanotubes that on your barbecue. In your barbecue, you have a few nanotubes you're eating. So it's probably more. You're probably getting more in your barbecue than you ever get from these sensors. But I don't think it's a problem. We would like to have the whole sensor array. I showed you things where we evaporate gold. So we have an evaporator. It's easy. It turns out that the company that's doing this, they have plastic substrates with that have a lot of carbon, and they're combustible, right? So you can basically throw them and burn them, or so ideally it will be that case. But I don't think it's going to be like cigarette butts lining the floating in Boston Harbor. I hope not, anyway. That there's nothing to have a consumable like this.
So in olfaction, there are about maybe more than thousands of receptors involved even for one sensing, and also there is amplification mechanism. So
yes.
In your case, how many carbon nanotubes are generally involved in single sensing unit, and also do you need any amplification mechanism here?
Well, so the nanotubes themselves, I mean, because you're running electrons around the circuit, you get to kind of signal average. That's a way to get gain. So in olfaction, okay, that you have many receptors, you may have duplicates. We actually usually do, when we put our sensor arrays, their minimum is usually 16 different sensors. We put redundancy in, that gives you greater reliability, and you can use it, again, to get some signal averaging that way. And so that's the way we think about it. We use the redundancy and signal averaging, but there are some, there are probably other clever ways of doing this, of getting more information out. I mentioned field effect transistors. I mean, nature is beautifully on this, that when your receptor fires, you have an ion channel that opens up, but then eventually those will depolarize, right? You ever notice that if you have a really strong smell, there are two things. I mean, I think about this because you'll get a strong smell, it'll go away. Now, there's two reasons. One, your brain may just decide that I don't like this, I don't want to listen to it anymore. But it could be that you're depolarizing those ion potentials, and so they're kind of shutting down and becoming less effective.
And no more?
We do have a reception. I think that's what.
Exactly.
I think that's the priority
Exactly.
right now.
Okay, so please join me in thanking our speaker again. Our program calls for closing remarks, and if anybody wants to make some closing remarks, looks like it's me. Well, let me be quick then. What a delight it's been, at least for me anyways, because it's been a rich program. And we really see how I think very much the Dreyfus Foundation, through its activities, is helping to indeed achieve its motto of what it's about. Now, again, please, everybody, join me and let's go to the reception and enjoy.